Good day. Today I'm going to talk about stochastic utility assessment, and specifically the mid-value splitting technique. Let's say today's your lucky day. You have a choice. You can flip a coin, and if you call it, you'll win $500,000. If you don't call it, you'll win $200,000. Or the other choice is flip a coin, and there's a 50-50 probability of winning $1 million or winning nothing. Now, you're only going to get to play this game once, and you have to choose one game or the other game. What would you do? Well, I know what I would do. I would definitely go with this game here, because for certain I'm going to walk out with at least $200,000, and with a 50-50 probability, I might win $500,000. Whereas over here, there's a 50% chance I'll win nothing. How would you feel if you selected this alternative and then lost? I'd feel terrible, because for that $200,000, I could pay off my house and have some left over, buy a new car, right? Contribute to my retirement fund. So clearly, this is a better choice for me. Now, what would Bill Gates do? Well, Bill Gates' financial situation is a lot different from mine. I suspect Bill Gates would go with this branch here, if he had a choice. Well, what does expected monetary value recommend? If we roll back the tree, 50% times 500 plus 50% times 200, the expected monetary value says 350. Likewise, the expected monetary value of this branch, 50% times 1 million plus 50% times 0 is 500,000. So if you're using expected monetary value as your decision criterion, clearly you'd go with this branch here. Well, how can we explain it that we would go with this branch, or at least I would? Well, to get the answer to that question, we can develop a utility function using stochastic utility assessment. This is a procedure that you can do on yourself or you can do on a client. It works like this. You give yourself or your client a choice between a spin, a lottery, versus a certainty equivalent. Now I'm going to plot the utility function down here, and I'll just do it for myself. And typically what's done is you start it between, you put the range that you're interested in working on, 0 to 1 million, 500,000 is in the center, 250,000 is the 1/4 mark, 750,000 is the 3/4 mark. And we usually start at the 50th percentile as the certainty equivalent. That CE is the certainty equivalent. So, this is the spinning wheel down here, like a roulette wheel. And we'll start out with a 50-50 probability on bliss or hell. What would you take, given this choice? 50-50 probability on bliss, 1 million, versus hell, 0, or the certainty equivalent? Well, clearly I'd go with the certainty equivalent. Okay, well then you split it this way. Change this, make it a little better. Okay, 75% chance at 1 million, 25% chance at 0. Okay, so it looks like this. It's a roulette wheel, where this is 1 million, this part here is 0. Well, still, I'd go with the 500,000 for certain. And you keep splitting this back and forth until you converge. I would probably converge at this point. Maybe 6% and 94. So to get me to split, in other words, the point where I'm completely indifferent between the 500,000 and the spin would be about 94% for 1 million, 6% on 0. Then I would be, I don't know. If I'm having a good day, I'd take the spin. If I'm having a bad day, I'd take the certainty. Well, what's interesting about this then is once you reach that indifference point, by going back and forth and searching for that indifference point with yourself or your client, once you reach that, then what we can say is that the utility value for 500 is the probability on bliss. Because if we roll this back, 0.94 times the utility of 1, utility is 0, 0.94 times 1 plus 0.06 times 0 is 0.94. So the utility of this branch is also 0.94. Because the utility on 0 is 0, utility on 1 million is 1, and now we can plot this point at 0.94. And then we repeat the procedure. Change the certainty equivalent to, say, 250. Go back and do the spins again. You reach an indifference point maybe at around 0.9, perhaps around here for 250. And do the same thing at 750. Go back and forth. Maybe you'll reach it at 0.96. Plot the point there, 0.96, or I guess it's more like here. Okay. And then you can do a piecewise linear approximation to the curve, or you can just eyeball it through those points. So that's the utility function. Well, once you've developed the utility function, then we can use it. What's the utility on 200,000? Well, we know the utility on 500,000 is 0.94. Right? We cross that out. Utility on 200,000 would be, what did we say earlier? 200,000 was 0.92, so 200,000 maybe was 0.90. 1 million is 1. 0 is 0. And then we roll it back using the utilities instead. 0.5 times 0.94, 0.5 times 0.90 gives us 0.92. Likewise, 0.5 times 1 plus 0.5 times 0 is 0.5. Now those are called the expected utilities then. And you always want to maximize your expected utility. So clearly, at least for me, I'm going to go with the 0.92 higher expected utility compared to the 0.5. So even though the expected monetary value is lower, the expected utility for this branch is much higher than the expected utility for that branch. And that's why I would go with this decision. So once again, back to this roulette wheel. You change these probabilities on bliss and hell until the person is indifferent between this branch and this branch. Once they reach that indifference point, well, that's the utility for that dollar amount, and then you can plot it. Now, the interesting thing about these utility functions is if you draw a straight line between the endpoints, that's called risk neutral. If a person is truly risk neutral, maybe Bill Gates is for small amounts of money, then you can use expected monetary value. But for most of us, for gains, most of us are risk averse. So any utility function above that straight line shows risk aversion. Now, people who have utility functions below that straight line, like down there, anywhere below it, they're called risk takers. They like to take risk. But most of us, again, for small amounts of money, or for any amounts of money, most of us are risk averse.